part 2 of looking at equilibrium and looking at energy and where things are going to end up for my chemistry class. So here, we're looking at the endothermic version of this. And again, you can see this is endothermic. Here are your reactants. Here are your products. And your products, when the reaction is over, there's more energy stored in those bonds, so there's a higher potential energy. So let's analyze this for a second. When you look at where your reactants are, and you look at where your activation energy ends, how there's extra energy that has to get into them, and when you finally get over the hump, oh, they're at a higher final energy. These are the processes that feel cold to you because you're investing energy into them, and then when they end, they don't give you that energy back. If you remember when we were in class, this is the one that we did with the barium hydroxide and the ammonium chloride. And the beaker got frozen to the wood block. And you get it took so much heat in and energy in from the surroundings that it actually got frozen to the little wood block or the cardboard that I had. So think about this. You're eventually going to get enough energy kicked in here that you're going to get some of these over the hump. I don't know how many. Yeah, arbitrarily we say 4. And so some reactants get converted into products. And so if we look at this, well, if we're not at equilibrium yet, and we're starting to go back and forth, we get some of these kicked over. Well, a couple of them are eventually going to get kicked back because there's less of a hump that they got to get over to get kicked back. And so I don't know where the final ratio of things are going to be, but it's not inconceivable that some of these molecules that are products are going to get back over that hump. Okay, well, let's switch the game just a little bit again, because I like doing that. And I'm not going to do this as many times as I did with my last one. And let's get some. And just to make it easier, we can do this by just putting this down a little bit. So if you look at this, my 2 curves, my reactants and products, and let me move this down just a little bit. Maybe right here. So first of all, the total energy difference between the two is not as crazy as my last drawing. Wrong color. Losing my mind. It's a migraine day, guys. By the way, if anybody's watching these in a year that I'm not teaching or somebody that's not in my classes, if you see me in sunglasses, I'm not trying to be a rock star, though I do like Bono from U2. I have a migraine. And so I'm just trying to keep extra light out of my eyes. So if you try to analyze this, well, it's going to take extra energy to get these. See? And I make more mistakes when I have a migraine. It takes more energy to get these reactants over the hump. Why? Further to go. But you're going to get some over. Yeah. Again, final amounts aren't as crazy here. But also note that these products have farther to go back now. They've got a lot further to go back. They've got a lot more oomph that they're going to need to get back over that hill. So maybe my first drawing was a little bit inappropriate. Maybe I should have had more getting over in the first place, because it's going to be a lot harder to get these guys back over that bump. So maybe when equilibrium establishes, there's not going to be as many getting kicked back over once you've supplied enough energy to your reactants. And so I could draw this where the bump is lower, and you're going to get a lot more back and forth for a while. I want to draw this scenario. So here, when you're looking at it, oh, the two energies of the reactants and products are pretty same. In fact, I try to draw them so they're equal. So the only thing different here is the bump to get over it. If you have enough energy to get over one way, you should have enough energy to get back. So it really shouldn't matter a whole lot if I'm there or if I'm there. You're freely reversible at that point. You should be able to go one way or the other. So what's the point when we're doing this? When we're talking equilibrium, you're talking about the ability to convert reactants to products and the rate of transfer between your forward reaction and your backward reaction, okay? When the reaction looks like it's over, it's just that the rate of something getting kicked over equals the rate of something getting kicked back. It's not impossible to go one way for the other. But when you are playing with simulations and you're looking what's going back and forth, understand it's got a lot to do with that bump and that energy to get from one side to the other. So try to show that with the drawings. I try to do that with the simulations that I posted online. But hopefully with a couple of the drawings that I put up and with this little talk here, that helps explain it just a teensy little bit. Okay? Be back with some other concepts later. Catch you in a bit.